Another form of chemical stress to a system in equilibrium can be in the form of changing the volume of the reaction vessel. And for gas phase equilibria, the Chatelier's principle states that decreasing the volume of the equilibrium mixture, so this is in the form of changing basically the volume of the reaction container, will lead to a shift in the direction that reduces the number of moles of gas. And if you increase the volume, then this will lead to a shift in the direction that increases the moles of gas. So at this point, I'd like to point out that we're only dealing with mass, or moles rather, of gases. Now, you might be given some questions in the test in which instead of volume, you're given pressure of a gas. So remember that for the ideal gas law, if we express it like this form, the concentration of a gas, which is given here as moles divided by volume, is actually directly proportional to pressure. So we may argue out that if we increase the pressure of a gas, and let's say for example that gas is in the reactant side, then the equilibrium should shift to the left, which basically reduces the pressure of said gas. Now, if you're considering gas phase equilibria, pressure and volume are actually inversely proportional to each other. So if you see problems such as decrease in volume, that's actually also equal to an increase in partial pressure of the gaseous components. And the same but opposite can be said for increasing the volume. Increasing the volume just means you're lowering the partial pressure of the gaseous components. Now, similar to concentration, solids and liquids, and this time aqueous solutions do not contribute to changes in volume or pressure, especially pressure, because these are incompressible anyway. So let's say, for example, if you have, and we cannot do this anyway in class, but I think this is an example found in your book, the dimerization of nitrogen dioxide. So first you have nitrogen dioxide in the reactant side. When it dimerizes, basically NO2 reacting with itself, NO2 has a characteristic brown color, but N2O4 is colorless. So if you decrease the volume of the container, at first you'll see a pale brown color of gases, but if you decrease the volume of the container, that color will become paler and paler, okay, until equilibrium is basically achieved. Now, if you do add this time an inert gas, okay, it does increase the total pressure of the system, but it does not increase the partial pressures of the gaseous reactants and gaseous products. So therefore, it doesn't actually change their concentration, and therefore the addition of an inert gas does not contribute to shift in chemical equilibrium. Okay, to illustrate, let's work on these problems from exercise 12-64. So I made some necessary corrections, by the way. There were a few typos in the problem, so added this, added that, and then also changed this into F2. All right, so for this one and for all cases, we are looking at increasing the volume of the container. So that's the chemical stress that we're actually introducing into the system. Okay, for working with gaseous phase equilibria, we first look at how many total number of moles we have on the reactant side. So we have 1 mole of nitrogen and 3 moles of hydrogen. So it's actually a total of 4 moles in the reactant side, okay? And then to the product side, I'm just writing this arrow to indicate that we're going from reactants to products. And then on the right side, we only have 2 total moles of gas. So as you can see, the number of moles of gas actually increases as you go from reactants or from products to reactants, but decreases as you go from reactants to products. Okay, so since increasing the volume will result in the equilibrium, will result in the system shifting towards the direction in which you produce more gas moles. So this reaction, upon introducing that stress, should shift to the left. Okay, letter B. So for letter B, we have 1 for the reactant side and 2 on the product side. So this one actually goes to the right when you increase the volume. Okay. Letter C, this time you have 2 moles of total gases in the reactant side, but also you have 2 moles on the product side. So there's actually no change in number of moles of gas. So this one's actually a no effect. Okay, so the equilibrium here does not change. Okay, or the position of the equilibrium does not change. And then letter D, that's also 1 going to 2. So this one is also going to go. This one is also going to go to the right. And then for letter E, again, we're only counting how many moles of gases we have. So on the reactant side here, we actually have 0 going to 2. So this one should also go to the left. Okay, no need again to worry about the solid. All right, and then the next thing that we want to discuss is changes in temperature. Keep in mind that an equilibrium constant K is only constant at a specific temperature. So therefore, the rule in general is if you change the temperature, you should change the value of K. Now, when that happens, we have to ask ourselves, okay, does K actually increase or decrease with temperature, or does it decrease or increase when you lower the temperature? Okay, so for that, to answer that, there's actually no universal rule, but instead we have to think of whether the reaction is exothermic or endothermic. Okay, let's say for example we have this reaction in which this blue complex ion, we're going to discuss complex ions in chapter 20, of cobalt, which has a blue color, is reacted with water. Okay, and as a result you actually now have this new complex ion of cobalt which has this time a pink color. So that's kind of an indication that the reaction proceeded. Alright, so this system is in equilibrium, but at higher temperatures, basically when you heat the system, you can see here that cobalt tetrachloride, or this blue cobalt complex, actually predominates. So the color of the solution is actually blue. Now that very exact same solution, if you actually chill it at room temperature, all the way down up until below room temperature, you will actually see that the predominating color is pink, meaning this formation of this pink complex rather is actually favored. Now one thing to note here is that this reaction, without considering this diagram, is actually an exothermic formation. Remember that an exothermic reaction will actually release heat. Okay, so it releases heat. And that's important when we discuss the effect of changing the temperature of a system, how it affects the system in equilibrium. So if you have an exothermic reaction, again, heat is released. So therefore, we can say that heat is a product of the reaction, as indicated, for example, here. Okay. On the other hand, if you have an endothermic reaction, heat is absorbed. So basically, heat is consumed when the reaction is endothermic. And by the way, please correct this. Delta H of an endothermic reaction should be positive. Okay, so here, we actually just treat heat as if it were either a reactant or a product, and then it's back to rule 1, which is effect of adding or subtracting products or reactants. Okay, so basically, if you have an exothermic temperature, okay, or an exothermic reaction rather, an increase in temperature, okay, will lead to an increase in heat, okay. So if you add more heat to if you add more products here, then therefore the reaction should shift to the left, okay? Which means that for this case, for an exothermic case, if you increase the temperature, then the value of K should drop, okay? Now, when you decrease the temperature for an exothermic reaction, then the reaction should shift to the right, basically to uncoat that heat. Okay, now for an endothermic process, an increase in temperature is synonymous to an increase in reactant concentration. So the reaction will therefore shift to the right, to the formation of products. If you have an endothermic process and you crank up the temperature, that will lead to an increase in the value of K. And the opposite is true. If you lower the temperature, that's analogous to removing a certain concentration of reactants, which will cause the reaction to shift to the left, and therefore a much lower value of K. All right, let's answer this problem 12.69. So according to this one, old-fashioned smelling salts consist of ammonium carbonate, and that reaction is endothermic, meaning heat here is actually part of the reactant side. And you're asked to comment here, okay, will the smell of ammonia increase or decrease as the temperature is increased? Okay, so an increase here in temperature will actually is synonymous to an increased heat. But this time, this case rather, note that heat is actually part of the reactants. So in order to get rid of air coat excess heat, you have to push the equilibrium towards the right, okay? And towards the right, you actually increase the formation of ammonia. So yes, this would actually lead towards an increase in the smell of ammonia. And then number 70, what if this time you have the following Kp values for the Haber process? Notice that as the temperature actually increases, okay, the value of K based on the exponents of these numbers, okay, actually decreases. So what happens is, therefore, for 12-70, so this just means that as you crank up the temperature, sure, K decreases, and that just means that the concentration of the products, okay, the concentration of the products is decreasing. So, and if the concentration of products is decreasing, then that must mean that the reaction is shifting towards the left as you increase the temperature, which means that heat is actually one of the products. So heat is also a product, and therefore this reaction should actually be exothermic. Oops. All right. And now lastly, we look at the effect of a reaction catalyst. So in general, the effect of adding a catalyst does not change the equilibrium mixture. Okay, it changes the speed of, or the rate of the forward and backward reaction, but the K value is still the same whether or not you add a catalyst. All right, so we are going to answer this online when we meet, but here's a good summary of effects of those stresses, chemical stresses, as well as this page.